Okay. So we're going to finish up the stuff on.
Imagine the same
phase
substance
changes.
existing as a solid, a liquid, and a gas, all at the same time. Sounds impossible, doesn't it? It's what's known as the triple point, and we are going to demonstrate it now. Any pure substance can exist in three phases. It can be a solid, a liquid, or a gas. We can show these phases using a pressure-temperature diagram called a PT diagram. This graph shows the location of the different phases of a pure substance in relation to pressure and temperature, with pressure P on the vertical axis and the temperature T on the horizontal axis. The three phases are separated from each other by so-called separation lines. There's a melting line between the solid and the liquid phase, the sublimation line between the solid and the gaseous phase, and the vaporization line between the liquid and the gaseous phase. The triple point is the location where all of these lines meet. It is specified by a certain pressure and temperature that is characteristic for each substance. If a pure substance is at these specified temperature and pressure values, all three phases will be present at the same time. One says that the three phases coexist. Pure water has a triple point temperature of 0.01 degrees Celsius and a triple point pressure of 611.5 Pascal.
The other thing to watch out
This is
for
the same as about 0.6% of the usual atmospheric pressure. At this point, water will exist both as ice, as liquid, and as vapor. Let's see what this looks like in practice. For this experiment, we need a vacuum chamber which is connected to a vacuum pump. A combined pressure and temperature sensor is connected to the hose between chamber and pump. It is also connected to a PC via USB, and values of absolute pressure and temperature in degrees Celsius can be shown on the screen.
More formal
Inside the chamber, we place a petri dish with liquid water. After the chamber has been sealed, the pump is switched on. Both pressure and temperature start decreasing immediately. During evacuation, the liquid water starts to boil as the pressure drops to the saturation pressure at the given temperature.
There is a different form. I showed you.
The glass beads reduce the splashing of water during boiling while the pressure decreases. They will also provide nucleation sites for the other two phases. While the pressure drops quite quickly, it takes longer for the temperature to approach values around 0.01 degrees Celsius. Unfortunately, our pressure sensor cannot measure below 1.2 kilopascal, but we will see later that the pressure is low enough as the water will be in all three phases. This can, however, take a few minutes. After some time, we see both formation of ice on the surface of the liquid water and that vapor bubbles appear in the liquid. We now have a situation where the water is boiling under a thick layer of ice. This is water at its triple point. All three phases coexist.
Negative change of enthalpy over R.
The different phases are, however, not in equilibrium, as the amount of water in each of the phases changes with time. When we switch off the pump, the water will be stable at the triple point as long as the chamber manages to hold the necessary pressure and temperature conditions. Once we open the inlet valve and increase the pressure back to normal, we can see that the vapor bubbles disappear first. Small droplets on the glass bell eventually evaporate and the ice in the petri dish begins to melt. In a second run of the experiment, we also place a small beaker with sulfuric acid in the chamber. The acid attracts water molecules from the gas phase and helps to improve the vacuum.
So we're going to look at the heating curve. And there's a lot of information we can get out of this. So first of all, what is it? It's as you're adding heat on the x-axis, adding energy, what is happening to the temperature of your substance? And so if we look at, we start with a piece of ice at minus 25 degrees C. It's very cold, and we haven't added any energy to it, so we start adding energy.
The steam produced during boiling eventually lifts the ice cap in a sudden motion.
The temperature shoots up.
The triple point of water is used to define the Kelvin scale. Kelvin is the unit for absolute temperature in thermodynamics and one of the 7 base units in the International System of Units.
And what's happening here is
at absolute pressure below the triple point, the substance cannot exist in its liquid phase. During condensation, for example, it will go directly from the vapor phase to the solid phase. This process is called deposition. We can observe this effect in nature. Fern frost can form on solid surfaces by the direct deposition of water molecules when the surrounding air is at temperatures below 0 degrees Celsius.
Until it hits the boiling point. So there it is, 100 degrees. That's where this next black spot starts. And then you're boiling. You're going from liquid to gas. So here it's all liquid. Here it's now all gas. This is like 50-50. So this whole line, you're adding energy. Temperature's not changing, it's just turning into a gas.
I'd like to thank you
now it's all gas.
for
now if you add more energy, the temperature
your evaluations. They were very useful to me. I already sent email to about 50 students, and I had some interesting exchanges with some of you. Many of you are very happy with their recitation instructors.
Okay.
That's great.
So
many are moderately
this curve
happy.
Here
Maybe
only
that's
shows
okay.
Temperature
But there are quite a few who are very
added.
unhappy with
at
their
100,
recitation instructors.
That's when it starts.
If you are very unhappy
transform.
with your recitation
I guess
instructor,
what's not
you are
listed
complete
here is
idiots
the fact that
if you
we
stay
have,
in that
I think,
recitation.
exactly 1 mole of ice.
We have 13
water.
recitation
And so,
instructors. And I can assure you that it will be
amount
very
of heat
easy to
added,
find
if you
one
take the
that
difference
agrees
here
with you.
From here to here,
You can come
I
and see
believe
me
is-
if that helps.
Yeah, it is 40 something.
Some are better than
47.
others. That's the way it goes
So
in
if you
life.
have a mole of liquid water, it takes 40.7
Some students
kilojoules.
Would like to
energy
see
to convert
more
all of
cut
that
and dry
water into
problem solving in my lectures. I think that's really the domain
So
of recitations.
there is
Lectures
a ton of information
and
you can get
recitations
from
are
this. First of all,
complementary.
this is water,
In
that's
lectures,
easy, but any
I
other
prefer to go over the
substance, you get
concepts,
melting points,
and I always
freezing
give
points,
numerical
whatever you call it,
examples to
and you get
support
boiling
the
points. You
concept
can
in a
identify
way
them very quickly.
that's problem solving.
The other thing you can get from this is notice
And I show
how wide this
demonstrations
part
to
is
further
versus how
support
wide this part is.
the concept,
Why
because
is this
seeing
one so
obviously
narrow
is believing.
compared to that one?
I try to make you see through the dumb equations, and admittedly,
solid
my
liquid
methods
versus
are
liquid gas.
sometimes somewhat different from what you're used to here at MIT.
Exactly. So here
I try
we're
to
only
inspire
weakening
you,
the IMFs so
and
that
at
they
times
become a
I
liquid,
try to make you wonder
molecules can move around.
and
Here we're
think,
completely breaking
and I want to
the
keep it
IMFs.
that way. I
And
believe
so
that
we're separating the
hardcore
molecules from the gas.
problem
Takes a lot more
solving is
energy.
really the domain
And that's
of the
why this is so much
recitations.
wider.
Many of you found
Another thing,
the exam
besides melting
too
points,
easy,
freezing points,
and
besides
many of you found the
the
exam
scale
too
of
hard.
the enthalpy of fusion
Some complained
here
it was too
versus the
hard
enthalpy
because
of
it was too
vaporization
easy.
here, is these parts.
Quite ironic,
So
isn't
we
it?
aren't going to focus on it right now.
They
but,
say we want more
we'll talk
math.
about it a little bit.
We want more standard
This
problems.
is the slope here. So this is
Look,
very steep. That is
Who wants
not
more
as
math?
Steep.
I'm teaching
This
physics.
is very steep.
I test you physics. I don't test you math abilities.
Is how much
If you
energy
digest
is
the homework,
required.
And that's
to raise
very
the
important that you make the
So
homework
notice that
part of
very
your
little energy
culture.
is required to
That you
raise
study
temperature. It's
the
really steep.
solutions. The
Whereas over
solutions
here,
that
it
we
takes
put
a
on
lot
the
more
web
energy
today,
to raise the temperature. It's
415.
less steep.
Solution to number 4 will go on the
What
web.
this is
Believe
showing
me,
you
they are
a
truly
property of a
excellent
substance called
solutions,
specific
not
heat
cut and
capacity.
dry. They give you a lot of background. If you
this is,
digest
a
those
property,
solutions,
that
then the
substance has.
concepts
It's
will sink in.
How much heat is required to change
And now,
its temperature?
at your 50-minute
Some things have very
test,
low
do you
heat
really
capacities.
want
Metals, for
problems,
instance.
which are
So the way you would
complicated
visualize
math?
this is pretend you have
Clearly not.
And I know the pot
I
is
could
made of
try
metal.
that
Say you have a
during
pot
next exam,
with water in it.
but then I may have to buy
Put it on the
myself
stove and you turn
a
the gas on,
bulletproof
whatever.
vest.
Takes
to be
forever
safe.
To heat up the water. All right? Water has
Concept
really high
is
heat
what
capacity.
matters.
It can store a lot of energy before
When I
the
gave my
temperature
exam
changes,
review here, I highlighted the concept. Each little
But
problem
if I
that I
take this
did
empty
here
pot,
was
just
extremely
put it in metal,
simple.
aluminum or copper, whatever. And I put it on
Conceptually,
the stove, it'll get hot
they were
really
not so
quick.
simple.
So
from a
metals
math point
have
of view,
a smaller heat
trivial.
capacity. It takes very little energy.
Clearly, I
to
cannot
make
cover
the temperature.
all the subjects in a 50-minute exam.
So that's another
I have to
thing
make a
this.
choice.
We're going to come back to
So
this.
your
We're
preferred
not a focus right now. Right
Topic may not be
now,
there.
understanding what you're seeing here is
Some of you think that the pace of this course is
by the
too
way,
slow.
these numbers here, this is
Some of you think
related
it's
to the
too
heat
fast.
capacity. So you're warming ice, changing its temperature.
The score,
you're changing
the average
temperature
score was
liquid,
3.8.
you're changing the temperature
4.0
of
would have been
steam.
ideal.
And
What do you want me
notice
to
it takes
do?
a lot
I
more
can't
energy to
accommodate
change the temperature
all of you, those who
of
think
water.
it's too slow and those who think it's too
Okay.
fast. 3.8 is close enough to ideal for me, 4.0.
All right.
And so
So
I have to leave it the way it is. Besides that,
as you can
keep
see
in mind,
from that
you
heating
are
curve,
now at
when
MIT.
something
You're
boils,
no longer in high
the
school.
temperature doesn't change.
Now the good news.
During the time it's boiling, and this makes sense.
There were
If
quite
I
a few
boil
students
some
who
water,
said the homework is too
put a
long.
thermometer in it, it's going to read 100 degrees. It's not going to
Not
go
a single person said
Not until the water's gone.
it was too short.
And then it'll heat up. Okay.
I
So
can fix
we
that.
have understood this already.
I
We
will
talked about
reduce
this.
all
The
future assignments
boiling
by about
point is a
25%,
result
effective tomorrow.
of
I have
the
already taken
liquid's
off assignment
vapor
number
pressure
5,
suddenly
2
now
problems.
equaling
You're down
or
now
being
to
greater
7.
than
And I will do
the
that,
pressure
all
that's around
assignments
the atmosphere.
that are coming up.
That's not something good. So if the
My
atmospheric
pleasure.
pressure is exactly 760 millimeters of mercury,
Today,
that's the pressure reading for today.
I'm going to cover
And
with you something
water will boil.
that conceptually
The vapor
is the
pressure of
most
water has
difficult
reached also
of all
760
of
millimeters
802.
mercury.
And you will need time to
At
digest
90
it.
degrees, it's only
And if you think
almost there, but it's not quite.
That what you're going to see is crazy,
Melting
not
point
alone.
is a little tougher to
the only
kind
good
of,
news is that conceptually
understand,
it's not going
internalize.
to become more difficult.
the way boiling point is you can kind of understand.
Remember
so
that
melting point
Ørsted
is
in
the same, the
1819
temperature's constant when
discovered
something's
that a steady current
melting. But I did
produces a
mention
steady
that
magnetic
solids
field.
have a vapor pressure.
and that connected
So we
electricity.
haven't studied that, but
with
solids
magnetism.
do create gases.
A little later,
ice
Faraday
rays
therefore
will
suggested that
slowly
maybe a
shrink,
steady magnetic
leaving them
field
for weeks.
produces a
And that's
steady
because
current.
the solid water
And he did
molecules
many
turn into
experiments to
gas
show
at
that.
a slow rate,
Turned
but
out
they
not
are.
to be so.
And melting
And one way
is
he
when
tried
the
that
vapor pressure
is
of
as follows.
the solid suddenly equals
He had
the vapor
here
pressure of the liquid state.
Battery with a
That's how we get
switch,
melting. So that's a little harder to
and
kinda
here
wrap your head around.
he had a solenoid.
I wouldn't worry about that too much, but in
closes
case you
the
wanted
switch,
that same.
a current will
Like,
flow,
so this is how boiling works.
and
how
that
does melting work?
creates
Well, that's how melting works.
a magnetic
I'm not
field
going to test you on that part though.
in the solenoid. And that magnetic field,
So
maybe it runs like
next
so.
we're going to look at another
Depends
kind
on the
chart
direction
called
of the
a
current.
phase diagram. And
And so
to
now
understand the phase
he put
diagram,
around
first
this
let's understand
solenoid
what an equilibrium is.
loop.
So there are many kinds of equilibrium. And
Let's call this loop number
equilibrium is
2.
going to be the focus of
So it was around the solenoid, and let's
you
call
might
this
like
loop
it, you might
number
hate
1.
it. But
of which
in an
the solenoid is
equilibrium,
part.
You've got this condition where two
Whenever there
things
was a
can
current
occur.
in number 1,
So in a phase
he
equilibrium,
never
you can
managed
have
to see a
solid
current in
and
number
liquid.
2. If there is
So
a
the
current
solid
going in number
turns
1,
into
there is a
liquid, the
magnetic
liquid turns
field.
back into solid.
And that magnetic
This is
field
what
is
happens
seen, of course,
at,
by
like if you
the
if you
conductor
maintain
number 2 by
something
that
at
loop.
the
never
freezing
any
point.
current. So he concluded that
Yeah,
a
some
steady
stuff will
magnetic
melt,
field,
some stuff will
as
freeze.
produced
It's
by
kind of a
the solenoid,
dynamic. It's happening at
circuit
the same
1,
time.
does not
We
produce
talked about this with the
a
vapor
steady
pressure,
current
how things evaporate.
in number
you know,
2.
when you
But then
put
one day,
your lid on your container of liquid,
he noticed
evaporation
that
is still
as he
happening.
closed
liquid
the
is
switch,
turning into gas, but at the
he
same
saw a
time,
current
some
in
of
number
that
2.
gas is turning back into liquid.
And when he opened the
That's an
switch,
equilibrium.
again
When
he
they
saw a
happen
current
at the
in
same
number 2.
rate, that's an equilibrium.
And therefore he now
Chemical
concluded
equilibriums happen
that a
too.
changing
We're
magnetic
not gonna
field
focus on that this term.
is
That's
causing
223, like
a
I
current.
said.
Not
But,
a steady magnetic
you know,
field,
NO2
but
is
a
a
changing
gas
magnetic
that is
field.
generated by
And this was a
older-
profound
well,
discovery,
everyone does, but, you know, if
which
your car is
changed
not
our
working very well,
world,
it'll generate a lot
and
more.
it contributed
And
largely
NO2
to
is
the technological
because two
revolution
NO2 molecules will
of the
combine
late
together
19th and early
to make
20th century.
N2O4, which I think is the brown stuff.
A current,
This is what we know of as smog.
therefore an electric field, can be
And this is an
produced by a
dynamic
changing,
equilibrium. Like, so
magnetic
it's
field.
constantly, you know, two are coming together.
And that
making
phenomenon
this,
is
and
called
then one of these molecules will
electromagnetic
suddenly break
induction.
apart.
and
and there's
that
an equilibrium.
phenomenon
So
runs our
the
economy.
thing to
as you
remember
will
is that this
see
is dynamic.
in the
This
next
is, even
few
though the amounts
lectures.
don't seem like they're changing, there's constantly stuff turning into one side and stuff going to the other
I have
side.
here
So
a conducting
this is
wire.
it's very active,
square.
even though it doesn't look
Could
like
have chosen
it's
any other shape. Try to make you see
The-
three-dimensionally.
other thing
And I
is
approach
for these
this
phase diagrams,
Conducting wire with a
we're
bar
gonna treat
magnet.
them as a
A bar
closed
magnet
system.
has a magnetic
So
field.
we're not going to allow outside
running like
influences
so.
when we kind of discuss, well, what's happening to these.
As I approach that
to the substance in question.
that conducting wire,
in reality, it's very
moving the bar
complicated.
magnet,
There's
that's
other outside
essential. I
influences
can't
that
hold
will
it still, I
affect
have to
whether
move it.
Something's going to be a solid,
If I
liquid, or
come
gas.
down from above and I move it down,
we're going to treat
you're
these
going
as
to see a
closed
current
systems.
going
Basically, nothing else
through
is going to interfere.
this loop.
And so this is what a phase
And
diagram
that
looks
current
like.
will go into such a direction
I feel like
that it
that's-
opposes
I don't want to go
the
too much
change
into it, but
of the magnetic field.
the
The magnetic
axes
field
are
is in
pretty
down
consistent
direction and
for
it
the
is
phase diagram.
increasing as I
Like,
move the bar
look at
magnet
the
in.
temperature is
Then
on the
this current
x-axis
loop
and pressure
will
is
produce
on
a
the,
magnetic field which is in
y-axis.
this direction. And when you look from below,
the phase diagrams is broken up.
the current
into
will go
regions.
clockwise, producing
And
a...
as you can see, it says gas, liquid,
magnetic
solid.
field in
Sometimes
this
gas is written as vapor. Same thing.
If you move the bar magnet out,
And
then the
these
magnetic
are the areas at
field is
which, at a
going
particular
down here,
temperature and pressure,
then
at
the
which your
current will
substance
reverse.
is going to be present in
the
a certain
current
phase.
wants
So
to
if you're
oppose
here,
the change
at this temperature,
in
at that
the
pressure,
magnetic
your
field.
substance is going to appear
And
as
that's
a
called
gas.
Lenz's law. It is
The
the most
lines
human law in physics.
That you see, not the
Because
dotted
there's
lines, but the
inertia
solid
in all
lines
of
here
us. We
are
all fight
the
change at
phase
some level.
boundaries. So
Lenz's law
gas, liquid, gas,
is extremely
solid, liquid,
powerful
gas,
in
liquid, solid.
always determining in which
If you're
direction
right on the line,
these induced currents
then
will
you are going to be
run.
equilibrium
It is not
with
a
both those
quantitative
phases
law.
that the line
You
separates.
cannot calculate how strong
So
the
the
current
idea
will
is
be.
you can have
But it's
both
very
a
useful,
liquid
as you
and a
will see
gas
today,
existing at the same
to
time.
know the direction
you're right on that
of
line.
that current. That gets you out of all kinds of problems.
There is something called a
with
triple
minus
point, and
signs.
there could be more than one. A triple point is where three lines meet.
I now want to do a
and
demonstration,
if you're at the triple point,
which is very
all
much like
three of those different phases
what you see here.
exist at the same time.
I have here
You might wonder, how can you get more than one triple point? Well, there's not just one
A loop.
kind of solid sometimes.
that is the square that you
right?
see there,
We've
except
studied metals and,
that
and
it's not
solids.
one loop,
Some
but it is
metals
many of them.
have different crystal structures, right? Iron, we know iron does. We played with that in the first lab.
hundreds, doesn't matter.
Those different crystal structures are dependent on temperature, like we did
And what
with
we're going to
tempering and
show
all that
you
stuff. They're dependent on pressure.
Is
So you
an
can
ammeter
have different regions of solid, for instance.
that is connected. So there is somewhere in this circuit an ammeter.
The last one is the
I have a bar magnet.
oddest one.
And I'm going to approach
So
this
if
conducting
it's not
loop
clear, the line
the bar
that
magnet.
separates liquid
And you're going to
gas
see a current
ends
running
right
in
where
one
that point
direction,
is.
and when I
And
pull it
above
out,
that, there's
it
nothing.
will be running in the opposite direction.
And so
And
you
when
might
I
think,
hold
well,
my hand
how do
still,
you define
so that
what's
the
a
magnetic
gas and
field
what's
is
a
not
liquid if
changing,
the line stops.
no
Well,
current.
that's the thing. There is no more
going to see the
distinction
current
between
meter
gas
there.
and liquid above that point. And so we call that region
Here is my
above
bar
that
magnet.
point the supercritical fluid region.
I come close to this,
So that
conducting
point
loop.
is called the critical
notice,
point.
you see a current. I pull back,
You guys know what
current
a gas
is in the other
looks like.
direction.
You guys know what a liquid looks
Now
like.
I will
The
go
supercritical
faster,
fluid has
so that the
properties
change of the
that
magnetic
kind
field
of,
per unit time is
go with
stronger.
gas. And really
More
weird
current.
substances.
I go out fast, more current.
So let me
You see, it's the
show
change
you
of the magnetic field that matters. If I come in very slowly, which I
some
do now,
videos of some of these things.
very slowly,
So
almost see nothing.
Supercritical fluid.
Right now the entire magnetic field is inside this loop.
The
strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current.
And the reason why it's, well, the caffeine dissolves in supercritical CO2.
So an
really
induced current
well, and then you can drain
is
the
clearly
supercritical CO2
the result
from the chamber.
of
You can just let the CO2
a driving force.
evaporate, turns into gas.
There must be,
and you're left with
just like
pure
we had
caffeine,
with batteries in the past,
which you then
there must
sell
be an
to Coke
EMF.
or Monster or whatever
there must be an
company
electric field
does their drinks with
that is
caffeine.
produced in this.
So this is
conducting
supercritical
loop.
critical CO2. I guess I
And
should
so
show you this.
I
before we
create
go.
now an
So
induced
on the left,
EMF.
we have
We
the
used that
triple
word
point,
EMF
or sorry,
earlier
the
for batteries.
phase diagram for CO2.
So now we have an induced
And you can
EMF,
see
which is the
that
result of this change in
one
magnetic
atmosphere,
field.
This is the pressure we exist
And that
at.
therefore
That's the one we like.
is the induced current
Our
times the
temperature
resistance
is somewhere over
of
here.
that
So
entire
this is 31, so right around
closed
here. And that's what room temperature is
conductor, whatever is
like.
in there.
CO2
In
exists
this
as a
case,
gas for
the
us.
total resistance of all
If
these
you were to
windings of all
lower
the
the
copper
temperature,
wire. That's Ohm's law.
it turns into a solid.
So the
There's no liquid.
induced EMF
And
is
that's
always
why
the
dry
induced
ice,
current
when you
times
put it in,
the resistance.
some water, it doesn't melt, it's sublime. It
Faraday
comes
did a
directly
lot of
back to gas.
experiments.
So to
And one
get
of
it
the
to
experiments that he
supercritical,
did
you're going to have
was
to
that
pressurize,
he
increase the pressure
produced a magnetic
way
field
up here.
So he ran
that's
a current.
What this chamber I'm going to show you is going to look like. This is some supercritical CO2 under pressure.
He ran a current.
And I believe they're just playing with the temperature to kind of shift it back and forth between that weird liquid and weird gas.
And he was switching the current in and out. So
kind of a combination of the supercritical fluid.
And so it produces a magnetic field. And this magnetic field changes when you
I don't know what's going on.
Close and open the...
Hold on a second.
The switch. And then here...
Some video is playing in the
background. He had his second
I
conducting
don't know how
wire.
This guy. All right. I like his videos, though. Those are good. If you like physics. Okay. I don't remember. The old guy with crazy hair. He does good physics lectures. So, here we go. This one is not so great. So, you've got your a line that's physically drawn, and you can see that the CO2 liquid is boiling, and the level of liquid is dropping. This is a normal phase change from liquid to gas. That's what you normally think of. And so you have a gas, or maybe you don't have a gas. Maybe it's a supercritical fluid. It's hard to tell. And then I think they're going to play with the pressure here. Yeah, so it's not condensing. Like when you condense something, you get droplets forming, and you get and the liquid kind of comes back through droplet form. It doesn't do that. It does this weird thing, and now the liquid's coming back. This one is a little better. This one is going to show liquid going to a supercritical fluid. And I know that it's a supercritical fluid because if a liquid turned into gas, you'd see it boiling, and you'd see the level go down. But now, yeah, it's a little boiling, but watch this line here, liquid to gas. It just kind of, hold on, just disappears. The liquid level doesn't shrink as it turns into gas. The liquid just kind of, that boundary is just gone. So that's a supercritical fluid where you don't get this distinct transition between liquid to gas. It just kind of melds away into something that looks like a gas or maybe like a liquid somewhat, you know? That's the supercritical fluid. They're weird. They've got amusing properties, though. I don't have any good videos of it, but there's like an old, grainy video on YouTube that shows using a sieve, which is like a porcelain bowl that has tiny, tiny holes punched in it, like really tiny. And liquid CO2 will not go through the holes. But as soon as you turn it to supercritical, it then just drains through the holes. It's weird. So yeah, I don't know. They supercritical fluids have slightly different properties than regular liquids or gases do. Anyway, let's save this one. So plasma is different. We're not going to study plasma, but plasma, you've heated up a gas so much that the electrons are now free from the atoms, or at least the valence ones are. I don't know if all of them are, but yeah. So in a plasma, you've got basically nuclei and electrons that are just free from each other. Yeah. There it goes. There's nice supercritical fluid, and it's going to come back into this is weird stuff. Anyway, all right. Before we do more stuff, let's show you. That's not the one I wanted. Cyclohexane. Oh, I know what was missing. So this is a demonstration of the triple point. How you can have a substance that is both solid and liquid and gas all coexisting and going back and forth. So right here we've got some cyclohexane, and it's under a small amount of vacuum. So there's a pump connected to the top, and I think it's near room temperature. I don't know how cold it is. You can see it's forming skin. There's a solid. So there's liquid underneath and a solid on top. It's just not quite the triple point yet.
It's the whole thing just gone. Oh.
So it's boiling now. You've got some liquid and solid on top, and it's boiling. Here it goes. is weird. So
I was about to say, I think the whole thing's solid, and now it's...
there you go. There's perfect. It's hard to get it to maintain that perfect pressure and temperature, but yeah, they got it a little bit.
Oh my god, okay.
So they're trying to get to that perfect triple point, that spot where the three boundaries meet. There's one for water too. Here, let me see. This one's not as exciting, but at least it's something real.
Brilliant is the best place to learn science interactively. It gets you hands-on to help you learn by doing.
Yeah, so this one is definitely in a vacuum chamber. You can't see the chamber itself, but there's like a bell jar on top. And so they got some ice and water in there. So I believe that for the triple point of water, I forgot to look at it, it's a pretty low pressure, and I think the temperature needs to be near 0. And there it's starting to boil. And this is at a higher speed, so that's why it's moving weirdly. Yeah. This one's not as exciting, but it's just weird that you can have all three at once.
So it should eventually just boil off, right? Because it's in the bell jar, so it's got a lot of room to...
Yeah. I mean, if they're maintaining a... yeah, there you go. Some ice forming too. So yeah, it's hard to maintain that pressure when you have something that can generate more pressure, you know, as it turns into a gas. Yeah, it's boiling underneath that skin of ice.
So do you have just like pockets of like have like a crystalline structure and then they evaporate suddenly?
I assume so. I mean, the thing is, you can't get perfectly on that triple point, so they're kind of fluctuating. I don't know. It's not perfect. What do you see?
I watched that bike video.
Oh, this one?
Yeah.
Oh, God. All right. We can save that for another time. All right. So here's another thing that's interesting about phase diagrams, or at least the ones we're going to see. Water is, as far as I know, the only one that has a negative slope for liquid to solid transitions. Everything else, like CO2, everything else has a positive slope. So think about what that would mean, though. If I have some ice right here at normal pressure, and it's, -1 degree. It's a little colder than regular, boiling, the melting point. It's a little colder, but right here. And all I do is increase the pressure. So if I increase the pressure, what happens to my ice? It melts, which is weird. So if I increase the pressure in my ice, it'll suddenly melt. Whereas everything else, if I have it as an ice, right, like solid form, and I increase the pressure, it stays a solid. And so what's happening here is water, and you know this, water is more dense than ice is. Ice takes up more space than water does. If I freeze some water in a container, that container will break open because the ice will expand and break your container. So the idea here is when water, and I'm not going to draw anything that's perfect at all, but when water freezes, you have to have your water molecules in these crystalline structures, but in a structure where negative is next to positive. You can't have negative next to negative, right? And so the crystal structure for ice has all these large gaps in it because that's the way the water molecules have to arrange themselves. And so ice takes up more space than liquid water does. And so the idea here is the increase in pressure generally means you're trying to force the molecules closer together. And so in this case, if I force the molecules closer together, I'm breaking these solids and I'm making it liquid because it has to exist as a liquid. The water molecules have to kind of, flex away, move around to get away from to being too close to each other. So that's water only. Water is, one of those things that is, ice floats on water. Everything else that is solid will sink in their liquids. So water is unique in this case. So here's the idea. An increase in pressure favors the phase that occupies less space. And that's water. Water, in this case, occupies less space than ice does. So what would you be expected to do yourself is I could give you one of these phase diagrams with no labels on it other than the axes labels. And you would have to tell me which side's solid, which side's liquid, which side's gas. I mean, it should make sense to you. Look, think about, when do gases exist at high temperatures? So the section that has the high temperature, that's going to be your gas. Low temperature is going to be your solid. High pressure means you're forcing things to occupy less space. That's going to be your solid. And then liquid's going to be in the middle there. You also need to be able to understand what happened. Well, first of all, the different points, critical point and triple points. The other thing you'll have to do is understand what happens to a substance as I change the temperature or change the pressure. So I could give you scenarios. I've got a substance that has this phase diagram, and it's currently at this temperature and this pressure, and if I increase the pressure to this, what happens to the substance? You would say, it starts as a gas, and then it condenses. The transition here would be condenses to a liquid. Or maybe it doesn't even go past this boundary. Maybe it goes past that critical point, and you would say it turns into supercritical fluid or something. So just being able to describe what's happening to the substance as your temperature or pressure is changing. So let's try this yourself. I think this is page 95. The questions actually start after Model 3, I believe. So you're going to have to skip a few pages after 25D. And honestly, some of these questions are pretty easy, but they get a little harder. So don't be insulted. Don't feel patronized too much, hopefully. Is it a? So you have to turn the page all the. No, D, not C. Yeah, here. Yeah. What page did we start?
96.
96, 97, yeah.
97, sorry.
So this is a case where you've got two different crystal structures that a substance can take. So based on the pressure, based on the temperature, you could have a more compact face center cubic, or maybe it's a less compact body center cubic, or something that we didn't learn. Yeah.
Because when you increase the pressure, it's kind of squishing everything.
Mm-hmm. I mean, one really obvious version of that is carbon's phase diagram. You're going to have graphite, you have diamond in there somewhere. Yeah, and then regular soap, right? So different allotropes, different ways you can.
Oh yeah.
Because diamond has been pressurized the most.
Yes.
We didn't talk about it with two sides.
Or like for the speed it takes to help the height.
And liquid at the same time.
So, to be clear, the substance is not a solid and a liquid at the same time. You have both existing in the same place. That's like a molecule is not going to be a solid and a liquid at the same time. It's you have a bunch of molecules. Some of them are solids, some of them are liquids, and they kind of swap places and stuff.
Yeah, thinking about it as a structure, kind of.
Sorry.
Thinking about it as like a structure, like which types can exist.
Well, I mean, there's no order to it. I think I wouldn't say it's like crystalline. There's not. It's just you're going to have chunks of solid and some liquid, and some of the solid is going to be melting, while some of the liquid's going to be freezing at the same time. That's it.
So the correct way to state that would say that the substance exists in all three or exists in
In
those
two different.
phases.
Yep. Or is in equilibrium with two phases. Yeah. There is a special phase of something that exists as both a solid and a liquid at the same time. That only occurs on like the moon of one of the moons of Saturn or Jupiter or something like that. There's a special phase that they theorized occurred, and they found it, and it's water, where the oxygens are in solid form, they're stuck in a crystal lattice, but the hydrogens are ionized, and they're now loose, and they're in liquid form. So the oxygens are stuck, and the hydrogens are loose. So it's both solid and a liquid at the same time. So that is extreme conditions required. So yeah, that's not what we're learning at all.
I can't say it now. Einstein concentrate, is that what it's called? Like when you get the temperature low enough.
That one's different. That's where the nuclei, I think, like just all the fuse together, and you get right. It's like it's what neutron stars are. I think. I could be wrong, but that's a little different. This one's just a solid liquid, like hybrid. It's weird.
Would it be conductive? If the no, because the hydrogen would be free, so the positive charges would be free.
Yes, well, so it's kind of like what a metal is like, but instead of electrons in it, it's the hydrogens. Yeah.
And then
Yeah.
from B to C, but it wouldn't still be the same thing.
Yeah. Theory again.
From A to B to C.
Yeah. It always gets intensive. Okay.
Yeah, this is different. This is more of a quantum thing, but I don't know enough about this to comment on it. Particle physics, Here, I wanted to look up something else. Come on.
have the different Romans.
Uh-huh.
What is that?
These are different solid crystal structures. Like water.
Yeah, pressure.
The ice crystal. Yeah.
For 7.
Yeah.
Wow, you're telling me it has 10 different structures that connect?
I mean, this might be outdated. I don't know, but they just keep finding more, like some more ways that water. I mean, water is a little special. It's very non.
Right.
I won't say it's not symmetrical because it is, but it's not round like an atom is. It's got a weird shape. Which I think there's a lot of different ways you can put water together.
It's really unique.
I mean, there's plenty of molecules that are weird shapes, but yeah, water is one of the more studied ones because it's so important. Yeah. Okay, let's. Maybe I'm rushing you guys. Oh, we'll see. But I want to show you guys this, and don't worry, you won't see this in an exam. But so there is that phase diagram in your activity that had 2 different kinds of solid. Well, you could have a ton of them. This is actually water. And with a little bit more pressure that you can see. We've got our vapor, gas, we've got our liquid area, and then we've got all of these different crystal states of water. So ice 1, and there's actually 2 forms of ice 1, ice 1C, ice 1H, ice 11, ice 9, ice 15, there's tons of them. And there's like little tiny regions where, it's just different crystal structures, different ways water makes a solid. And it really depends on the pressure and the temperature. They may not exist at room temperature. Like once you make them, maybe they won't exist at any other pressure. But yeah, there's what's funny about this is like, I won't say it's modern, but it's very recent. If you like sci-fi, there's a science fiction author named Kurt Vonnegut. He's very famous for writing Slaughterhouse-Five. That's a good one if you want to try it. But there's another book called Cat's Cradle, and in Cat's Cradle, I vaguely remember this. The scenario was a scientist invented a new form of ice called Ice 9, and I see there's an Ice 9 here, but that's not that one. And this Ice 9 in the book was, the property of it was any water that got into contact with Ice 9 would immediately turn into Ice 9 as well, at any temperature. And the idea was it was a doomsday scenario. Somebody would drop Ice 9 in the oceans, and it would turn the ocean into Ice 9. So yeah, there's like sci-fi follows science, modern science at least, so they get their ideas. And this is from these phase diagrams. Anyway, Kurt, yeah.
It's cold enough, wouldn't ice pull in more water and kind of?
Yeah, normally it would. I think in the sci-fi story was once you made Ice 9, it was stable at regular temperatures, and so it would catalyze the transformation of anything into Ice 9, which is not true. I mean, but that was a nice idea. Anyway, so talking about these questions here, I think the first few of them are pretty self-explanatory, or at least you figured them out. And then you, again, we talked about how do you describe what's happening at these triple points, at these phase boundaries. The substance exists in both phases. You'll have some in liquid, some in solid, or some in one kind of solid. So at G, you're going to have a little bit of solid beta, you're going to have a little bit of solid alpha, you're going to have a little bit of liquid, and they're going to be in equilibrium with each other. So it's not going to be static. You're not going to have just these things and they're going to stay like they are. They're going to be constantly interchanging, going back to one solid beta going to solid alpha, solid beta going to liquid, and vice versa. So we looked at the critical point I. So again, I, that's the temperature and pressure above which your substance will become a supercritical fluid. There is no longer any, I won't say it's no distinction. You will not see any transitions between a liquid and a gas anymore. It'll be a gradual thing that you can't notice. You won't get condensation. You won't get boiling anymore. Okay, and so phase point G. Yeah, we talked about that. H, you have both solid alpha and vapor, gas at the same time. So starting at point A, going to point B, then to point C here, you would say that you have a gas, and as you increase the pressure, it remains a gas until you cross this line and it condenses. So use the right words. It condenses to a liquid, and that's it. And then the last question, I think you started at B and you go to D, E, and F. So you start with a gas, you decrease the temperature, and then suddenly it condenses. It turns into a liquid by the time you get to point D. And then as you get to point E, you get freezing or crystallization. Either one works. So the liquid freezes into a solid type alpha, and then F, it just keeps getting colder, but it stays the same kind of solid. Okay, so just knowing how to read them, that's really all you got to do. If we talk about density, what's happening with the density in these cases? Well, obviously, going from gas to liquid to solid, in every case except for water, your density is increasing. Solids are going to have a higher density than liquids. Liquids are going to have a higher density than gases. Gases have the lowest density. In water's case, the liquid density is higher than the solid density, okay? Let me back that up. Yeah, okay, let's leave it at that. Okay. I don't want to say anything. Let's leave it at that. We'll see a slide later that kind of confuses the issue a little bit, but we'll wait for that slide. Okay. This is another one, and I'll let you guys do it if you want to look at the slides. It's just another phase diagram for this one for bismuth, that funky metal that makes the little rainbow shimmery things that look like cubes. So that's bismuth, and I think only one of these does the shimmery cube things, but there's a lot of different forms. Okay. So if I were to ask you some questions about heating curves, for instance, how many transitions do you see in this diagram? We'll stop it there. Sorry if I cut you off. But most people are saying B, yes. There are two phase transitions. So the flat spots in a heating curve or a cooling curve going the other way represent the phase transitions. This is melting. This one is boiling. Okay? There you go. So if the graph below represents temperature versus time with a constant rate of heat input, which phase transition requires more energy? A, ice melting, or B, water boiling? All right, we talked about this already, so we'll stop it there. A versus B. It is the water boiling that does it. Excellent. By the way, this has time on the x-axis, but the title, or not the title, but the description says we're applying a constant heat input, a constant rate of heat input. So, over a certain amount of time, you get a constant amount of heat added. So it's the same as heat added, basically. But yeah, we've got a small, short line here, a much wider line here. This represents more heat required to cause the entire amount of liquid to boil. So it's the water boiling. And we already talked about this. The heat of vaporization is always going to be higher than the heat of fusion. So there we go. Okay, let's talk a little bit about water in general. as it relates to IMFs and all the things. We studied some of these. Water has a very high melting point and a higher boiling point than expected. So we know the reason for this now. It's because of hydrogen bonding. Water expands when it freezes. Ice is less dense than water. It floats. So we understand that as well. These strong intermolecular forces, the strong dipole moment in water causes it to solidify in a way that creates lots of empty space between the water molecules. And so solids are going to be less dense in this case. And so the ice floats on water. If it didn't do this, life on Earth would be a lot different, because floating ice gives you, in the winter, we get ice forming on the top of lakes, which insulates the rest of the water so the fish live. Because if it froze, if the ice was more dense, all the ice would sink to the bottom, and the lakes would freeze from the bottom up, and nothing would survive. At least not the way we think we know it. So life would be very different if ice didn't float. Water is an excellent solvent. I think we'll see a slide later that talks about this, but it doesn't dissolve everything, but it is something that dissolves more things than any other solvent. All right, water is a really good solvent. It has the largest surface tension of any liquid, except for mercury, because mercury is a metal. And because of the strong IMFs, it's got excellent capillary action. That is extremely important, even though it's not something we think about water doing a lot. But if you study biology, plants, that's how water gets through plant roots and through the stems of any plants. There's no pump. It just gets sucked up through capillary action. Your blood vessels. Yeah, we need our heart to pump blood through the large arteries, but the little tiny, tiny capillaries that get the blood from the larger arteries to like the rest of your cells, the heart is useless there. It's all capillary action. The blood is pulled through using capillary action. That's why they're called capillaries. So liquid water has a very high specific heat. So we talked about what specific heat, specific heat is a short version of specific heat capacity. But we talked about that. That is the idea that water requires more energy to change temperature. So the consequences of that is that water is a good heat sink. You can store a lot of energy in water. What does that mean to us? Well, if you've got a lot of bodies of water, you're living near a lot of bodies of water, the temperature is more, the climate is more temperate in those regions. And that's because in the summer, those bodies of water will absorb energy so that it won't get too hot. And in the winter, those bodies of water will release some of that energy so it doesn't get too cold. Water is a good storage mechanism for energy. We can't really use it for anything else, but you know, that's what it's used for in the environment. So there we get some glaciers, only possible because ice is less dense than water. I don't know if that one exists anymore, but there's a picture. So yeah, there we go, because of density. Come on, clicker. Oh, here's another just a density thing. So water has a higher density than ice does, but anything else, and here's just an example, paraffin, liquid paraffin, has a lower density than solid paraffin. So solid paraffin sinks in liquid paraffin, whereas solid water floats in liquid water. So that's normally what happens. So here's a picture that I think is interesting. This part of this temperature versus density graph is pretty common to everything. As you increase the temperature of a liquid, so that's what's happening here, you're increasing the temperature of your liquid, I would expect the density of the substance to go down, because what's happening is at the higher temperature, your molecules have more kinetic energy. These molecules that want to vibrate, move around, it's harder to get them to get close together. They have too much kinetic energy. So the density is going to go down. So everything behaves like this. But let's look at that very, very first part. This is for water only. That very, very beginning has a curve that goes up and then down. So this is what's happening when you have ice and it suddenly melts and it turns into a liquid. Well, ice has a density of, well, yeah, it's right there. And so as soon as it melts and you give it a little bit of energy, well, now those water molecules that used to have all this separation between them, they can now move around and get closer together. And so suddenly, for a little bit, they get more dense. Until you give them a lot of energy and then they're too excited, they're moving around too quickly, and then they'll be less dense again. But this is unique to water. Only water has this initial rise in density when you melt it. Okay. So the universal solvent, we can dissolve organic substances in water. We can dissolve ionic substances in water. Yes, not everything, but it dissolves a lot of things. And because of that, plants live, nutrients go everywhere. We also pollute water, and we pollute pollution everywhere because of water and the groundwater, but you know, that's how it works. So this is a nice, I wish I had this picture before, but this is a nice picture that just demonstrates capillary action. So you've got this little device that is a tube that is an L-shaped, and you fill it with some water, and this is just colored just to see it. And gravity, you fill it up to here, and if capillary action didn't exist, you would have the exact same height of water in every single tube. Okay. And these tubes are getting narrower and narrower and narrower as you go to the right. But what's happening here is water likes glass. It's attracted to glass surfaces. So as that tube gets more narrow, and really all there is glass surface for water to interact with, the water rises higher and higher and higher in these glass tubes. And that's demonstrating capillary action, this idea that water really likes glass and wants to stick to it. And so it's slowly going up. All right. We talked about specific heat. So the formal definition of specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. That's it. So if you look at water's specific heat capacity, it takes about 4 joules of energy to heat up 1 gram, that's like a milliliter of water, by 1 degree. So 25 to 26 degrees, basically. Or 30 degrees to 31 degrees. There's 1 degree change. But compared to like any of the metals, it takes very little energy to raise a gram of that metal by 1 degree C. And so that's unique for water. Water can store a lot of heat before it changes temperature. If you have ever looked into hot tubs, you probably haven't, but if you ever like, oh, what would it be like to own a hot tub? It takes a lot of electricity. It takes a lot of energy to heat up water. You can't use one of these outlets because there's not enough power coming out of it. You need the equivalent of 4 of those put together. Yeah. So 2 220 volt circuits mixed together is what's required to heat a hot tub. Those are 120, 110, right? You need 4 of those. So 220 volts, like the big ones that your dryers use. 2 of those. That's how much heat is required to heat up that much. Like that, it's not even a lot of water. Hot tubs are, they're not that big. So think about a heated swimming pool. That'd be even worse. Yeah. It has to be indoors. Otherwise, outdoors, you'd be losing all that energy. So, so water is, very unique. It's got all these properties, and we can understand them all now because we understand IMFs and the difference between waters and others, okay? All right, any questions about liquids and IMFs and all that? Because we're going to move on. That's okay. If you have any more, come back. We'll come back to it. But let's talk about gases now. So we've started talking about gas. We started talking about pressure. We haven't really talked about what it is exactly. We started talking about the kinetic molecular theory, but not a whole lot. So we're going to get into this a lot more. And I will admit that the gases section, I think it's easy to understand the general concepts of gases and how they behave. What gets tough is when you start doing the word problems, like that, I have a gas that is at this pressure and this volume, and I do this to it. What is the new pressure? So some of those can be easy, but they can get pretty gnarly too. So we'll try to take that one step at a time. We're not going to do that today, but we'll start with the gas chapter now. And first we'll talk about how do you describe a gas. So liquids and solids, pretty easy to describe. You can give their mass pretty much, and that's it. That's all you really need. But for a gas, while you could give a mass of a gas, it's very difficult to get the mass of a gas. Like gases, you can't put them on a scale. Not very easily, at least. So we have other things that we can use to describe a gas, the state of a gas. And you will need at least 3 of these 4 properties to fully describe a gas. Because once you have 3 of them, you can get the 4th one. But you need 3 of these. So volume. And the typical unit for a gas volume is liters. It doesn't have to be, but that's what we're going to use a lot. So if in doubt, convert to liters. Temperature. And the standard unit for temperature of a gas has to be Kelvin. No question. You have to use Kelvin. You cannot use Celsius. It will not work. And you definitely can't use Fahrenheit. So for a gas, this is the one time we're going to force every temperature to be in Kelvin. And it's not optional like liters is. You have to use Kelvin here, okay? For pressure, this is a little bit optional like volume and liters is. The standard pressures you're going to see lots of them. We like to use atmospheres a lot because it's nice, easy to understand. What atmosphere, that's what we like. But the SI unit is the Pascal. So you'll see that. You'll see millimeters of mercury. You'll see a lot of different units. So get ready to be able to convert between them. And then the last one, numbers of particles, which is the mole. We're not going to use literal numbers of atoms or particles. We're going to use mole amounts, okay? So we have numbers that are not crazy.
What's the conversion from Kelvin to Celsius? It's like plus 200 or something, right?
273.15. So that's what we're going to go to next. A Kelvin scale and the Celsius scale are exactly the same. A 100-degree change in Celsius, 0 to 100, is the same in Kelvin. It's just 2 different numbers. It's 273.15 to 373.15. So 100-degree change. They have the same scale. They just start at different places. In fact, we call Kelvin an absolute scale because it starts at 0, and that's the lowest temperature. Whereas Celsius is a relative scale. It's based on the freezing and boiling point of water. Whereas Kelvin is based on the fabric of reality. 0 is the lowest temperature you can have. Although that's debatable if you're a physicist, because they can claim negative kelvins, which I don't understand. It's weird. Anyway, we'll talk about temperature in a little bit. Fahrenheit, we are used to it because that's what we use for weather, but it sucks in science, so don't use it. So here are the conversions, and I don't like that one. The proper Celsius to Kelvin conversion, it is Kelvin is equal to degrees C plus 273.15. That one's exact. That's an exact conversion. That one's not, so you're introducing sig fig problems if you use that one. But this one's exact, so you only have to worry about sig figs for your Celsius or your Kelvin in this case, okay? These are actually also exact too. Celsius to Fahrenheit, Fahrenheit to Celsius. Those are exact. This is exactly 32, so it's not 2 sig figs, it's infinite sig figs, okay? So when you're converting between Fahrenheit to Celsius and then Celsius to Kelvin, however many sig figs you had for your Fahrenheit, that's how many sig figs you're going to have for your Kelvin. Well, sort of. You remember you're adding, so you get different rules for adding. Okay, so oh well, no. Yeah, it's different. It's weird. You'll see. I'm not a big sig fig stickler. We're not doing intro to chem. That's where I crack the whip. But here, just be reasonable. All right, so let's talk about pressure. So before I introduced pressure as a way to think, the way to think about pressure is numbers of gas particles. The higher the pressure, the more gas particles you have. And that's true. We just saw with the phase diagrams, the higher the pressure, the less space between the particles. Yeah, that's true too. But the way you should really think about pressure, the additional way you should think about pressure is, so let's look at what the SI unit is. The SI unit is the Pascal, and it's a derived unit. The base SI units are like what? The kilogram, the meter, the second, and the mole, and there's candela, which we don't use as brightness. But there's very few base units, so everything is a derived unit. It's built off of other things. So a Pascal is a Newton per meter squared. So a Newton is a force, and I'm struggling to remember exactly how Newton is. I think it's a kilogram meters per second squared. Yeah, it's mass times acceleration, I think. Yeah. So kilogram meters per second squared, but it's a force. And over meter squared is an area. So a pressure is a force applied over a particular area. That's what a pressure is. And so the way, if you want to visualize it, I like the mattress example. So if you lie down on a mattress, your body weight is a force. So if you weigh, let's say, 150 pounds, that's the force your body's applying on the mattress. But where are you applying it? You're applying it over a large area. If you calculate the area of the body, the part of your body that's touching the mattress, it's a pretty big area. So a force applied over a large area is going to give you a low pressure. But if I stand up on the mattress, that same force, your body weight, is being applied over a small area, just the area that your feet occupy. And so a force over a tiny area is going to give you a large pressure. And you can see the results when you lie on a mattress versus standing up on a mattress. So you're sinking a lot further in the mattress when you stand on it. If you're lying on it, the mattress doesn't sink very much, right? Your body is pretty well supported. So that's kind of how I like to visualize pressure. But again, pressure is really a gas. I mean, we're talking about gas pressures. So the atmosphere applies pressure. Think of the amount of air that's directly above you. That air has mass. It has a weight. It's applying a force to your head. And that force is a pressure of 1 atmosphere. The closer you are to space, so if somehow you're way up here, there's less air on top. There's less mass. There's less force on top. So you're going to feel less pressure the closer you are to space, the higher up on a mountain you are. So that's pressure. We have many, many units. Here's 1 atmosphere is equal to 760 millimeters of mercury. Torr is exactly the same as millimeters of mercury. It's just another, it's a different unit, but it's the same. Pascals is the SI unit, but notice that 1 atmosphere is 101,325, right? That's what that means. It's a big number. So often we don't really see pascals, we see kilopascals. It's a lot easier to write 101.325 is the conversion. Besides these, there's PSI. PSI stands for pounds per square inch. In the old days, we thought of pounds as not a mass, but a force. Pounds over square inches. Square inches is an area. That's exactly what a pressure is. And I believe atmospheric pressure in PSI is 14.7, if you care. But we'll give you the conversions. So all of these conversions I will give to you, don't worry. So how do we measure pressure? So we've seen other instruments, but this particular instrument is how we measure atmospheric pressure. This is a barometer. And an old school one. This is not how we do it now, because this is full of mercury. It's pretty dangerous. So it's very critical that you understand how the barometer works, because then you'll have a good understanding of what pressure does. So what a barometer is made of is a tube that is closed at one end, And originally this tube was completely filled with mercury. So you fill it complete with mercury, put your thumb over the opening, and then you have this pool of mercury. You turn this tube upside down, you stick it in the pool of mercury, and then you let go. Well, mercury is actually not too bad on your skin because it doesn't absorb. It's the breathing in part that's the bad part. And remember, every liquid has a vapor pressure. So even though it's low vapor pressure, it's still making vapor. So if you play with mercury in a closed space, you're going to breathe some of it, a little bit. So anyway, when you let go, gravity, this was originally filled, gravity is going to take over and it's going to pull this mercury down, right? It wants to be the same height as this pool. But it doesn't go all the way down. It stops here. Why would it stop here? Well, what's replacing the mercury in here? It's not bubbling, this is completely submerged. Air is not getting in. And the naive answer would be, oh, the vacuum stops it. But the vacuum is the absence of anything. There's nothing there. There's nothing there that's going to stop it from coming out. So why is it stopping right there? Well, the idea is the atmosphere is pushing down. It's applying a force on the surface of this mercury pool. If this mercury level goes down more, where does this mercury go? It goes into the pool. What will happen is the level of the pool will slowly rise. So the atmosphere is pushing down and is countering the rise of the level of the pool. And so the strength of the pressure, the strength of the atmosphere, the pressure that the atmosphere applies, is balancing out the weight of this mercury that gravity is pulling down. So that balance is reached. And when you measure what's the height of this mercury column from the pool to this level here, it's 760 millimeters. So that's where the unit comes from, the millimeters of mercury. And that's where the 760 comes from. So think about that, 760 millimeters, that's 76 centimeters. That is right here. That's this high. So it's a pretty big measurement device, right? They're pretty big. If you wanted to make a barometer from water, you could do that. But remember how dense and how heavy water is compared to mercury. Mercury is really heavy and really dense. If you wanted to do the same thing with water and have gravity pull water down and compete against the atmosphere pushing on the pool of water, your column of water would have to be 33 feet high. So you could make a barometer using water, but your column would have to be 33 feet high for, so if I tried doing this with water, the water would just stay right at the top. I wouldn't get any vacuum here. I wouldn't get anything dropping out. It would have to be at least 33 feet high before the water would start dropping down a little bit.
Someone's obviously done that.
Maybe. 33 feet high, that's a lot. That's like 3 stories high, right? So yeah. Anyway, mercury is ideal because it's so dense and heavy, all right? But it's not ideal because of it's so toxic. So the other tool is the manometer. And so the other one is used just for atmospheric pressure. This is for measuring the pressure of any container of gas. There's 2 ways to use a manometer. This is one. So this is an open-ended manometer, where one side is open to the atmosphere. And so the idea is the atmosphere is pushing on this level of mercury right here. And on the other side, we connect our container of gas. And this gas has a pressure, and it's pushing on that side of the mercury. If the pushing is equal, if the pressures are equal, then the levels are going to stay the same. And the idea is, well, the atmospheric pressure and the pressure inside this container are exactly the same. But if they're uneven, let's say the pressure inside the gas is higher, inside the container, is higher, then it's going to beat the atmosphere. It's going to push this level of mercury down. This level of mercury is going to go up. And this height difference between here and here is the difference in pressure between the gas inside that container and the atmosphere. So how would I calculate the actual pressure? Well, it's going to be the atmospheric pressure, so the pressure from the barometer, plus that change in the mercury height. And it sounds like we're mixing units, but we're not. The pressure is in millimeters of mercury, and the difference in height is in millimeters of mercury. So it's a pressure. It's a length, but it's a pressure. It's weird that way. If it's going the other way, if the gas pressure inside the container is lower, then it's not a tug of war, but then the contest is going to the opposite way. The atmosphere is going to push harder. And to get the pressure inside here, we're going to do the pressure of the atmosphere. And this change in height is going to be a negative value now. And so we're going to subtract from the atmospheric pressure, and we'll get the pressure of the gas inside. Yeah?
What if you use like real thick tubes of mercury, 2-inch thick tubes?
Oh, you mean thicker than this?
Yeah.
It will not matter. You'll still get the same height difference because the larger surface area is more area for the atmosphere to push on, and you still have this, and then the weight of each sides are going to be even until they the heights will be the same. It's just works. Yeah. Again, we do not use these tools anymore because of mercury, but it's good to understand how this works so that you want to have a good grasp on what pressure is. So if I were to ask you, I've got this gas cylinder attached, or gas sphere container attached to a manometer. What's the pressure inside? Be very careful. Okay, we're all good. So, as expected. So the actual answer is D. And the reason for that is look at the units. So centimeters. We need millimeters. So 25 centimeters is 250 millimeters times 10. So 750 plus 250 is 1,000. Yeah. So be careful.
Do it again.
Anyway, it's okay. When you make mistakes like this, you remember it, and you're like, I'm never going to do that again. So that's good. So this is just, hey, make sure you know how to do conversions. And just in case somebody has difficulties with conversion, I'll do these right now. But if I have a pressure of 722 millimeters of mercury, I want instead in millimeters of mercury. If I want it in atmospheres instead, I'm going to set up a conversion factor. Well, millimeters of mercury is in my denominator, so that these two cancel out. I want to convert to atmospheres. That means it needs to be in my numerator. And then I look up the equality. 1 atmosphere is equal to 760 millimeters of mercury. So this is telling me I divide. And if I divide those two, I will get 0.950 atmospheres, 3 sig figs. These are exact conversions, so the only thing we have to worry about is our starting value, 722, 3 sig figs. The next one, if I have 0.63 atmospheres, then I want to convert to kilopascals. I need the atmospheres to go away, so I'm going to put that in my denominator. I want kilopascals in my numerator, so that's what I end up as my answer. 1 atmosphere is 101.325 kilopascals. That's exact too. So 2 sig figs in my answer. And so when you do the math, you get 64 kilopascals. Okay, so just some basic conversions. You're going to have to get used to doing this because there's going to be word problems where you're given a pressure in a unit that you don't want. You want a different unit. So be ready to do conversions. And so have these conversions handy. I will give them to you on a quiz or an exam. Okay? Oh, we're a little early. Okay, so let's start this just so we have something to do. We're going to look at how gases behave in general, and we're going to start with the Boyle's law, which is one of the oldest laws. And I'll be honest, it's possible that somebody discovered this centuries before in other civilizations. This is very Western-centric. So, yeah. So that's what we've got right now. But Boyle, in 1660, discovered the relationship between pressure and volume of a gas, okay? So he kept the amount of gas, the number of moles, and is going to be the number of moles usually. So the amount of gas is the same, and the temperature was the same. He just varied pressure and watched volume, or varied volume, watched pressure. And he found that the volume and the pressure were inversely proportional. That means that when the pressure went up, the volume went down, and vice versa. Okay, both of these mean inversely proportional. So any pressure times the volume always equaled some constant. So it was always the same. So if I took the same system, it had to be the same gas, same number of moles, same temperature. I could vary the pressure and the volume would change, and it would always equal that same constant. Okay. So that's not really the best version of the equation. That's not, or I should say, that's not the most useful form of the equation. So if a pressure times a volume is going to give you a constant, you could basically say, well, I've got one pressure and one volume, and if I change the pressure to something different, I'm going to get a new volume too. And they'll both equal K, so why don't I just leave K out and just say pressure 1 times volume 1 is equal to pressure 2 times volume 2. What this is a quick equation that lets you solve for changing the state of a gas. So if I keep the pressure, I keep the temperature and the number of moles, the amount, the same, then I can look at how pressure and volume change. So over here we've got Boyle's law in graph form. So we've got pressure versus volume, and this is true. This is how it relates. As the pressure goes up, the volume goes down. You get this curve like this. So that's not a direct relationship. That's an indirect relationship or an inverse relationship. To get a direct relationship, to get a straight line, you would instead plot 1 over volume versus P, or the opposite, 1 over P versus volume. Okay. So yeah, that one gives you a direct relationship. So normally it's an inverse relationship. So some real life examples of Boyle's law is done for like these kinds of setups. You need some kind of sealed container that can change volume. And this is our cylinder and piston setup. So the cylinder is a container, and the piston goes in and out to change the volume. So here we've got a gas where we're not changing the amount. It's the same amount each time. And we're keeping the temperature the same. How do we do that? Maybe we keep it in a water bath that's at a certain temperature or something like that. But if you do that, then as you decrease the volume, the pressure goes way up. As you increase the volume, the pressure goes way down. So going back to the earlier, like how we thought of pressure, the higher the pressure, the closer the molecules are to each other. That's kind of pretty visible in this picture. Okay. All right, so that's Boyle's law. We'll come back to Boyle's law in a second. Over 100 years later, we have Charles's law. You don't worry about the dates. I don't care at all. This is just kind of for interest's sake. And Charles looked at the relationship between volume and temperature in a gas. And this was actually pretty important because it revealed something new, which we'll get to in a second. So one example of Charles's law that I can give to you is if you ever seen a balloon that's been blown up and then you cool it. You put it on dry ice, or you pour liquid nitrogen on it or something, and it shrinks. As you decrease the temperature, the volume shrinks. And that's exactly what this guy found. He didn't use balloons, but I forgot what experiments he did. But he managed to find the relationship, and the relationship says that as the volume goes up, the temperature must go up as well. Or as the volume goes down, the temperature must go down. There is a direct relationship between volume and temperature. And again, that equation is not as useful as a different form, and that should be K lower subscript c, Charles' law, where instead you take the volume and temperature of a gas at a certain state, and that will equal the volume and temperature of a gas at another state. So basically, I have a volume and a temperature of a certain gas. If I change the temperature to something new, I can calculate the new volume. Or if I have a volume and temperature of a certain gas, and I change the volume to something new, I can get a new temperature. Again, the conditions for Charles's law is that you must have constant pressure and constant amount, moles. Balloons are good for that because the pressure inside a balloon, since the walls of the balloon are flexible, the pressure inside the balloon is the same as the pressure on the outside. So the pressure inside the balloon is always going to be atmospheric pressure.
You said that goes for both Boyle's and Charles, that it has to be constant.
Well, so for Boyle's law, the temperature must be constant, and the number of moles must be constant, because you're changing the pressure and the volume in Boyle's law. Oh, yeah.
Yeah, so theoretically, if you had a balloon with water in it, there'd be no evaporation happening once, in the balloon.
Yeah, I guess so.
Well, if there's a little pocket of air at the top,
Yeah, I was
there'd
gonna-
be an equilibrium point that would be reached.
I-
Someone would be evaporating and someone would be going back in, right?
I wonder if you manage to fill the balloon with no pockets of air at all, maybe over time it would develop a small pocket of water vapor. But I don't know if you could see it. Maybe it'd be too small. Maybe at room temperature it'd be too small, but if you heated it up to a certain temperature, it might make a pocket. It's a very difficult experiment to do because first, water has a lot of air dissolved in it, and so some of that will come out. And two, you need a balloon that was completely impervious to air. And balloons do admit they're porous a little bit. Yeah. Yeah, I don't know. I haven't thought about that, but maybe you could see the vapor pressure that way. I don't know. So this is what I wanted to show you with Charles's law. When he did his experiment, he couldn't get like super sub-zero temperatures. It didn't have liquid nitrogen or dry ice. So when he did his experiment, he was limited to really cold day temperatures or like maybe ice or something like that. So his temperatures didn't go down. He didn't get all the way down here. But when he did his plots of temperature versus volume, he got all these straight lines. And if you redo it, you'll still get other straight lines with different amounts of moles. You're just going to get a bunch of straight lines, and they won't all be exactly the same slope. But what happened with all of them is that they all, if you extrapolate all the way to like a certain temperature, he didn't know Kelvin either at the time, he only knew Celsius. If you extrapolate them all to super low temperatures, they all crossed here. And that was the origin of absolute zero. There was this minimum temperature that every one of his graphs hit. When you get to zero volume, which is impossible, but when you extrapolate your data all the way down to zero volume, they all cross the line at negative 273 Celsius. And that's the origin. I mean, that's the start of absolute zero. There must be some minimum temperature that you could reach, and that's it. So there you go. Yeah. So this is a theoretical thing at his time, because can you get zero volume physically? Not really. I mean, you've got a gas in there, and when you shrink the volume, you're forcing the molecules closer and closer and closer together. But eventually you'll hit you can't shrink it anymore. So it was just the theory at the time. We've since proven there is an absolute zero, I think. I don't know the exact experiments. So the last one, we'll do this one quickly, because we'll talk about the math next week, is Avogadro's law, or hypothesis in this case. And there's actually other ones we're not going to talk about, but this is another major one. And in Avogadro's law, he looked at the relationship between the amount of gas and the volume, so moles versus volume. And this one seems a little bit obvious to us, okay? But remember, this was before they really understood the concept of an atom very well, right? I think this was just the beginning. I forget, Dalton's law was... I'm trying to remember the dates. This was near the beginning, okay? So it's pretty simple. As the number of moles of a gas goes up, the volume goes up, assuming you keep the pressure and the temperature constant. All right, yes, you can change all of those things, but then it's harder to predict what will happen, okay? But if you keep those things constant and you just vary the number of moles, you will get, so you double the number of moles, you will double the volume. Here's the most obvious example. If I have a balloon that has a half mole of helium in it versus a balloon that has 4 times the amount of helium in it, the volume will be 4 times as large. And again, this form of the equation isn't as useful as a form where you're looking at, okay, I've got a gas at a certain state before, I do some change to it, and now what is the new volume? So, for instance, volume 1 over number of moles 1 is equal to volume 2 over number of moles 2. This one is less obvious how useful it is, but when we get to reactions, so like we'll do examples where you'll make a gas, and we're going to look at the stoichiometry. Like this reaction for every 1 mole of this generates 3 moles of gas, and so the volume went from 1 liter to 3 liters because the number of moles of gas went from 1 to 3. So this is a very important one, although it seems so obvious. So we'll stop there because I don't want to go too far into it. This is like the basics. This is the beginning. We're gonna complicate things further. We're gonna combine these laws into one. Call it the ideal gas equation. We'll study partial pressures. So what happens when you mix different gases together? We'll look at the densities of gases. We'll look at the speeds of gases. So we're going to look at the kinetic molecular theory again. We'll look at this concept of real versus ideal. So some gases, doesn't really matter what identity they are. They all behave similarly. But under more extreme conditions, it matters what gas we're talking about. Some gases have more IMFs than others. Some gases are larger than others. And under extreme scenarios, those will start to have a role. So we're going to look at all those things next week. Okay. Have a good weekend.